Okay, so let's move on to lecture 10. In this lecture, we will be exploiting the concept of Riemannian metric we defined in lecture 7, to study a bit the distances on a Riemannian manifold. So the first concept we introduce today is the one of minimal geodesics. We have a Riemannian manifold, Mg, and if it is Riemannian, it means that on every tangent space we gave a scalar product. So we defined a way to compute the norm of every tangent vector. Therefore, we can define the length of a curve. Let me just recall that the length with respect to metric G of a curve gamma is simply the integral over the interval where gamma is defined of the norm of the tangent vector to gamma. So So the norm of gamma dot with respect to G is the square root of G of gamma dot. Obviously, G at the point gamma of t. So G on the tangent space at gamma of t, so a point of the curve. So we have our curve at some point. We have the tangent space to the manifold where the curve lives. So this is the tangent at the point gamma t to the manifold M. We have the derivative, gamma dot, and on this tangent space, we have our scalar product, G at gamma t, which allows us to compute the norm of the tangent vector to the curve. This is a function of the parameter t, obviously, because as t varies on the interval, the point travels on the supports of the curve, so we change the tangent space, and we change, in principle, also G. Okay. Now, the distance between 2 points is the infimum of the length of all the curves that go from one point to the other. And is an infimum, it's not a minimum in principle, because I probably gave you an example. If you remove, if you take a subset of R2, like the disk, and you remove the origin, the distance between 2 points opposite with respect to the origin is directly Euclidean distance, but you don't have a curve of that length that joins the 2 points, because you cannot travel through the center which you removed. Okay, a curve is a minimizing geodesic if that infimum is a minimum. So, a curve is a minimizing geodesic if the length of the curve is the distance between the two endpoints of the curve. Okay? It is not obvious at all that minimizing geodesics exist. For example, the plane minus a point. Now, this is a minimum problem, so we could try, and it's a minimum on functionals, because it's a minimum on functions. So it's a minimum of a function, integral functional, which is defined on continuous functions from, well, C infinity functions from the interval to a manifold. So we could write down Euler-Lagrange equations. We want to minimize the length of the curve gamma. So we need to find a minimum if it exists. Euler-Lagrange equations give necessary conditions. So they will give you, I think you all know them probably from like mathematical physics, some instance of mathematical physics. If you don't know them, the easiest thing is to look them up on Wikipedia probably at this point. But in anyway, you have a function. So you want to minimize the length of the curve gamma. So you fix gamma of A equal P and gamma of B equal Q. And so you take all the, let's say, C infinity functions or piecewise C infinity functions such that gamma of A equal P, gamma of B equal Q, and you define G of gamma as the integral between A and B of the square root of G gamma, gamma dot in dt. What we said before. This is a function which depends on gamma here and on gamma dot here. Euler-Lagrange equations tell you that if you want to, if you're looking for minima of this functional, you can search among the zeros of a certain differential equation. Now, Euler-Lagrange equations work in Rn, so we will be working in local coordinates because Euler-Lagrange equations are a differential equation, so a local condition, a condition that holds at every point locally, not a global one. So we don't care about the manifold at this point. We just take local coordinates and do computations in local coordinates. We will get a differential equation that has to hold at every point of the curve in local coordinates. Actually, if we do things right in any local coordinates. So, again, we take our local coordinates and we write xj of t instead of xj of gamma of t. xj is the function that gives you the jth coordinate. So it will be a function of t. We will forget that it's always a function of gamma of t because we are living on the curve at this point. Now, our functional S, in principle, S could depend also on t in the Euler-Lagrange theory. So S of t, x dot, because gamma becomes x and gamma dot becomes x dot, is the square root of Gij xi dot xj dot. It's the same thing, just written in local coordinates. Again, remember that Gij is the matrix of our scalar product in the local coordinates we chose, with respect to the local frame that these coordinates give. When an index is repeated, we mean that we are there is a summation on that index. So here there is a summation on both I and j. It's a usual bilinear form. Now we have to compute the derivative of this function with respect to every xh and with respect to every x dot h. And then the derivative in x dot has to be derived also with respect to t. Euler-Lagrange equations tell you that the minima of this functional are to be searched for among the points where this derivative is equal to this double derivative. Okay? Now, this is just an easy computation. If you here the only dependence from x, which I recall that it's the curve, are the coordinates of the curve. So the only dependence here from gamma is in g. So when we derive this, this expression with respect to any xh, we derive only the g term. And so we end up with this. Okay, this is the derivative of the square root, and then we end up with this. If we derive with respect to a dot variable, we just derive this part, which is a product. So easy again is just like this. And then we should derive in t. There is no 2 here because you derive once this variable and once this variable, and you get the same result when you sum up. So now, to compute this time derivative, it's better to parameterize gamma with respect to arc length. That means we can always do that, and that means that the length of the curve is given by the parameter t. So the length of the curve up to some point, gamma t, is t minus a. This is that it's parameterized. So the gamma is parameterized with respect to arc length if the length of gamma restricted to an interval a s is equal to s minus a. So how long you travel on the curve is how long you travel in the parameter space for every s in. And if you have never seen something like that, it's easy to obtain this parameterization. I mean, in principle, it's easy, because you compute the length depending on t, on the end point, and you invert this function and you do a substitution. So it's just as easy as that. You have a function length with respect to t, you invert the function, you compute t with respect to length, and you substitute everything. There's your parameterization. In practice, inverting the function is not at all easy, but in principle, it's an strictly increasing function, so it's invertible smoothly. Okay, so if we parameterize with respect to the arc length, it means, okay. And that means, sorry, I mean, if the integral is just, so the length is just the difference between the endpoints of the curve. So it means that we are integrating the function 1. So that means that the tangent vector to the curve has constant norm 1. Okay? So in our situation, it means that our S is always 1 in t, okay, in t, not in the other variable. I mean, it's constant as a function of t. So we can just remove it, and it's constant as a function of t, so here we don't need to worry about this term. It could be also parameterized with respect to a multiple of arc length, so S is constant K and whatever, but anyway. Now, when we derive this term with respect to T, we can derive G or X dot, and we end up with, I mean, here is the chain rule, and here is just the deriving twice X, so we get dot dot. Okay, so here are the two terms, and Euler-Lagrange equation tells you that you get a minimum of this functional if, only if this term is equal to this term for every h, for every coordinate. So we can write down, okay, maybe. So we equate this term with this term, and we write it down as a proper differential equation. So we isolate the term x dot dot. Okay, so x dot dot is equal to this term plus, minus, this term. Now, to get rid of this GHH, you should remember, write it here, but won't use it. Nope, okay, whatever. I won't write it here. You should remember that the inverse of GHH, the matrix inverse, is just GHH with the indices above. So we multiply everything with GIH with the indices above. And you get to this equation. So the index changed because I don't have enough letters, but you have double dot variable equal to, this is the 1/2, the other term, the one that came from the derivative with respect to the x variable, minus the term that came out together with this one when we took the time derivative of the dotted variable. Now you just need to rearrange things. You can, okay, this was a common factor. I don't know why I wrote it split up. And now there is a small trick. This term, well, it's symmetric in I and H, so you actually get to split it up, and you end up with this expression. The first two terms come from this one. So because it depends if H is the second or the first one. Actually, it doesn't matter because the metric is symmetric. So in the end, you can write this term as a sum of two terms of this form. But anyway, this is a computation in local coordinates, so believe me. You also can regroup the xi dot, xj dot, and you could recognize this term, which is the Christoffel symbol of the Levi-Civita covariant derivative. So you end up with this equation, x dot dot equals to minus gamma x dot x dot. So a curve, gamma, is a geodesic, not a minima, a geodesic, if it satisfies the equation, the equation above. Where gamma I, this time I wrote it explicitly with gamma I, which is the ith component of gamma with respect to local coordinates. So, this is the geodesic equation. Okay, this differential equation, which has to hold in every coordinate. I explained to you the derivation in terms of Euler-Lagrange equation because I think it's quite nice, but it doesn't matter. If you didn't really grasp this part, whatever, just know that from functional analysis, if you want to minimize the length, you end up with this local condition, which is the differential equation in every coordinate, which involves the derivatives of the metric tensor. So the derivatives of the matrix of our Riemannian metric G. It's called metric tensor usually, which altogether give you the Christoffel symbol, which, too many which, came up in writing in local coordinates the Levi-Civita connection, which I recall you, I recall for you that was the only connection for which the parallel transport is an isometry and which is without torsion. Anyway, it's unique and it's determined by the metric. Now, some results about the existence of geodesics. That's a differential equation, so you can apply all the machinery about differential equations. It's not a linear differential equation, but, I mean, people studied also other kinds of differential equations, for example, elliptic differential equations, like this one. So for every point and for every point in M, there are a neighborhood of the point and a bound epsilon, such that for all points in the neighborhood and for all tangent vectors which are not longer than epsilon with respect to our metric, there is a geodesic starting from the point with initial vector that one. Okay? So we do not only have to limit the set of points, so a small neighborhood, but we also have to limit the initial speed, velocity actually, of our geodesic. But if we don't overdo, geodesics exist. Second, for every P, there is a neighborhood where you can connect every 2 points with a geodesic of length at most epsilon, and that is a minimizing geodesic. So locally, you can find, locally geodesic are minimizing geodesics. If you look small enough, the equation we found is also enough to guarantee that that's a minimum, at least for close enough points. 13, if you have a curve which is parameterized with respect to arc length, and this curve gives you the distance between the endpoints, that is a geodesic and hence a minimizing geodesic. So it satisfies the equation, and then obviously it satisfies the condition for being minimal. The important point is that it should be parameterized with respect to arc length. Now, this was the, I won't say low level, but the coordinate version of the geodesic equation. So we have a condition, we look for a minimum of a functional, and we write down the Euler-Lagrange condition. We end up with the differential equation, which luckily I think it's elliptic. So you know that the theory gives you local existence for short times, whatever, and you can prove that locally geodesics exist, and locally they are minimizing geodesics. Now, from a higher viewpoint, we consider a connection. If you struggle with the concept of connection, just think that a connection gives you a way to get the directional derivatives of vector field. So the main point of after this slide, the main point of having a connection is having a covariant derivative. Covariant derivative is a way to differentiate a vector field along a tangent direction. So I have a vector field, I have one point and one tangent direction, and I can say what is the directional derivative of the vector field along that direction. That's the main point. And these covariant derivatives in local coordinates are a part which is just partial derivatives of the coefficients plus a correction term which involves the Christoffel symbols. Now, we defined the covariant derivative for a vector field on the whole manifold, or at least on an open set. Now we'd like to talk about covariant derivative just along a curve. Now, a vector field along a curve is a map from the interval, which parameterizes the curve, to the tangent bundle, such that at every point, the value of this vector field is above the point of the curve. This is the same kind of condition that you have for a section, that it projects down to the right point. So in practice, you have for every point of the curve, gamma of t, you have a tangent vector, x of t. Not the tangent vector to the curve, any tangent vector. So this is a vector field along the curve. So the curve is, in some sense, carrying around this vector. The covariant derivative along of x along gamma is defined in the same way. Is the second factor projection of the vertical projection of the differential of x applied to the only vector field that lives on the interval, which is d in dt. This could be written also as x dot. It's the same as gamma dot. It's the derivative on the interval. So on the interval you have just one variable, you can take only one derivative. So in principle, this function goes from the interval to the tangent bundle. So again, its differential goes from the interval to the tangent of the tangent bundle. Then we apply v, and we project to the vertical tangent bundle. And then we split it in a piece which is the tangent, and another we don't care about. We end up with this operator, which has this really weird symbol, so big D over dt of x. Now, this is all theoretical. In practice, many times, your vector field defined only on gamma can be extended outside. So if you are in this situation, the covariant derivative along the curve is just the usual covariant derivative of x in the direction of the curve, which is, what is the direction of the curve? It's gamma dot. It's the tangent vector to the curve. Just notice that this is a notation problem. This is defined as a function of t. This is defined in function of the point gamma t, but then gamma is parameterization, so it doesn't change too much. So anyway, if you don't want to think about a new operator, just think that this is the covariant derivative, which is, I will tell you again, covariant derivative is just in local coordinates, which I think maybe is the easiest way to understand it. The covariant derivative is a part which is the usual derivative plus a correction. So what does it mean? It means that you have here dixj, so the partial derivative with respect to the ith local coordinate of the jth coefficient of your vector field, plus a correction term. Which is gamma j. I never remember which is which. It's not important in the Levi-Civita, but in general. Well, anyway. So, what is this stuff? the first part is what you would like to do, okay? So these are the derivatives of the coefficients of your vector fields. If you have a vector function in Rn, the derivative is the Jacobian matrix, which is the partial derivatives of the coefficients of your vector. So this is the part you would like to have. What is the problem? The problem is that you have your manifold somehow with holes, whatever, blah, blah, blah. And you have your local coordinates. So here you have the coordinates of RK, which I'm drawing as a grid. And when you go back to your manifold, you have local coordinates, which will give you this sort of curved lines or whatever. The problem comes when you do computations in another coordinate chart which has its own local coordinates, which are different in principle. So here you have something like that. So you see, I mean, this is obviously a bad drawing, but on the intersection where they overlap, here, the green line and the orange line do not fit together. In fact, you know what happens here, because it's the function from one chart to the other, which is phi composed with psi to the minus 1, which is just a smooth function from RK to RK. So it's not the identity. Things don't glue up. It's a smooth function. So if you try and do this computation with respect to the green coordinates and with respect to the orange coordinates, just, I mean, think about that. If you derive if you change variables, you end up with what? With the, okay, you have to change variables inside the vector field. So how does the vector field change? The vector field changes by being multiplied by the Jacobian of the transition function. So you have, let's say, this function here. So this pink function transforms coordinates into coordinates. To transform coefficients of vector field to coefficients of vector fields, you have to use the Jacobian of this map. So when you change variables, you have to multiply all these coefficients by the Jacobian of the map, and then also take derivatives with respect to the other function. So you end up with the derivative of the composition and another piece, because you have a product, tangent vectors time Jacobian. When you derive the tangent vector, you end up with the same term in the other coordinates. When you derive the Jacobian, you end up with something which contains the coefficients of the vectors and some other terms, which is this term here. So this is the term that accounts for changes of variables throughout the charts of your manifold. You would like to do the first part of the operation. You cannot. You have to add something in order to define an object, a derivative, which is global on your manifold. Okay, I did this parenthesis because I know that the lecture on the connections was a bit foggy, let's say. I hope this is not as foggy. Probably not easy, but hopefully. Anyway, this part accounts for the change of local coordinates. and that is a connection, the covariant derivative. Now, what does it mean? Yeah, the last part. What does it mean to take the covariant derivative along y of some vector x? It just means to multiply all these parts by y, so it's di xj yi plus gamma j ih xh yi. Again, all the repeated indexes mean summation. And usually you have one up and one down. Okay? If they're not one up and one down, something went wrong. Or you are reading a careless book about Riemannian geometry where they implicitly use the metric tensor to raise and lower indices in any case of need. But anyway. So this, the covariant derivative itself is somehow the Jacobian. The covariant derivative along y is the Jacobian times y. Okay. So, moving on. Some properties of this thing, the covariant derivative along a curve it behaves exactly like the covariant derivative. So, it's linear. It obeys Leibniz rule. Obviously, for the covariant derivative here, you would have the differential of f. Here you just have f prime. Okay, it's just a one variable thing. And if you start from the Civita connection, you have the compatibility with the metric. If you remember the fact that the parallel transport is an isometry, means an infinitesimal relation, a differential relation, which is that the derivative of the scalar product is the scalar product between one covariant derivative and the other vector field. So, in this case, the derivative along the curve of a scalar product of two vector fields on the curve is the scalar product between one covariant derivative along the curve and the other vector, and the other way around. Again, if the vectors extend out of the curve, this is just the usual relationship we wrote down the last time, which was that the derivative along a vector field x of a scalar product is written in terms of covariant derivatives. So is it? Now, if you take x equal to the tangent vector of the curve, as a derivation, this means just deriving along the curve, okay? So the tangent vector defined by the velocity of the curve acts on the function deriving them along the curve. So this x of g is just the derivative of g along the curve. So if you write down everything as a function of the parameter, is d in dt. And these two are the covariant derivatives along the curve. So with respect to the tangent vectors of the curve. Now, if you recall from the other lecture, a vector field is a horizontal lift of gamma if it lies on the horizontal, in the horizontal subspace at every time. If its differential lies in the horizontal subspace every time. That means, in terms of this covariant derivative, it means that the covariant derivative along the curve of x is 0 constantly. We say that such a vector field is parallel along gamma. Why? Because along gamma, its derivative is 0 in some sense. So it doesn't change, at least along gamma. So it's parallel to itself at every point, in a way. And this is the other way of defining the parallel transport. So the parallel transport of a vector field, a vector x at some point gamma t0 is the vector x gamma t if the vector field defining both of them is parallel along gamma. So if its covariant derivative along gamma is 0. Now, a higher perspective on geodesics. First thing first, we need it to be parameterized with respect to arc length. It means that g gamma dot is constantly 1. So if you derive this function, you get 0 in t, because it's constantly 1. If you remember the formula, deriving a scalar product means g covariant derivative vector plus g vector covariant derivative. In this case, the vector is the same, so you end up with, okay, 2 times the scalar product between the covariant derivative of gamma dot and gamma dot. Remember that, notice that if we can extend gamma dot of t, and we usually can, this derivative along the curve is just the covariant derivative of gamma dot of t in the direction gamma dot of t. So what are we looking for? We are looking for the rate of change of the velocity of the curve along the curve, something we would like to call acceleration, something which is usually related to curvature, to how much the curve curves. So we need the scalar product to be 0 if the curve is parameterized with respect to arc length. So let's look at this term. In local coordinates, this term is it's a vector field. Its jth component is nabla j gamma dot, which is the part, the reasonable part, the partial derivative part. And you see that here the ith partial derivative is multiplied by gamma dot I, which is this gamma here. And then you have the correction in terms of the Christoffel symbols. Now, this term, okay, let's see. di gamma dot h gamma dot I. So this is you could write down, this is a function of t, but you could write it down as a function of the point on the manifolds, which is a function of t. So gamma dot j is a function of the coordinates of gamma of t. And this partial derivative is the partial derivative with respect to the ith coordinate. And then you multiply by the derivative of the coordinate with respect to the time. So you're writing down something like d in the xi of a function, well, okay, of gamma dot j times, well, not, okay, it's the same. Not really. Time the derivative in time. So this is just a chain rule. So you end up having gamma dot j. So this first part is gamma dot j, and the other one is just, it stays like this. So this, and this is, if you notice, this is just the geodesic equation. So therefore, gamma is geodesic, so this part vanishes if and only if these components vanishes. That means if and only if the covariant derivative of gamma dot along gamma is 0, or equivalently, if nabla gamma dot is 0. Which means that with respect to the curve, its velocity doesn't change as a vector field along the curve. So in some sense, it doesn't change either, not only the speed, so not only the modulus of the vector, also the direction of the vector. So it's something, in some sense, it's something, it's a straight line in a way. It's the generalization of the concept of straight line. Okay. The results then are the same as before. It's just a different way to write it down. Now, a consequence of this, the exponential map is an important tool. Okay. For a point and a vector, let's consider the maximal solution of the geodesic equation, which starts at that point with that tangent vector. You remember that if the point, for every point, we could find a neighborhood where this vector, where this equation had a solution if the vector was small enough. So we define omega, the set of P and V in the tangent bundle, for which we can at least get to time 1 in the curve. Okay? So we want to start from the point and go at least 1 in the parameter t. Now, this set is open, it's easy to prove, and it contains 0p is the 0 vector, okay? So the geodesic starting from a point with the 0 tangent vector is just the constant curve that stays in the point. So it always exists for every time. So this omega, for every point, it contains a small ball of tangent vectors around the origin. The exponential map is exp from omega to m, and it sends the pair point vector to the time 1 of the geodesic. So, which is also being parameterized with respect to arc length, the point at distance 1. At least it could be the point at distance 1. It depends. Gamma V0 is equal at P and gamma dot V0 is equal at V, obviously, both conditions. One is missing. X with P is the restriction of exp to one tangent space. So we start from the point that's fixed, we vary the vector field, and we go in every direction with length 1. And we see where we end up. Okay, this is called exponential because if you are in an open set of matrices, this is the exponential of a matrix. So the tangent space is again the matrices, and this is the exponential of a matrix. It also works for linear subspaces of matrices like symmetric matrices and some subgroups, so things that are closed with respect to operations, like the orthogonal matrices. So, for example, the tangent to the orthogonal matrices are the skew symmetric matrices, if you take the exponential, the matrix exponential of a skew symmetric, you end up with an orthogonal matrix. And the generalization of this operation is this exponential map from the tangent bundle to the manifold. Properties. The map is smooth and exp, so the restriction to a tangent space, so you fix the point and in every direction you go of length 1, is a local diffeomorphism from a neighborhood of the zero vector to the neighborhood of P. And the differential of this diffeomorphism in the origin of the tangent space is the identity. This means that exp is a first-order attraction. So remember from lecture 3, the Riemannian gradient descent, exp is a first-order attraction which is defined on every Riemannian manifold. And in particular, every submanifold over n with the induced metric over n. You can also invert the exponential. So the exponential goes, the exp goes from the tangent space to M. So you can define a chart taking the neighborhood of P and using exponential P to the minus 1 to get coordinates, because for every point on the manifold near P, you get a point in the tangent space. The tangent space is just RK, so you get coordinates. These coordinates are called normal coordinates, and they're very useful to do computations because geodesics are just straight lines in these coordinates. So geodesics from P, from the origin, are just straight lines, radii. The metric tensor, so the expression of the metric in P, in 0, is just the identity matrix. The Christoffel symbols in 0 vanish, so the covariant derivatives in 0 are just the partial derivatives, and the derivatives of the metric vanish. So normal coordinates give an approximation to second order of the Euclidean metric on your manifold. And okay, one last note, some equivalent things. If you can define xp on the whole tangent, if you can join every 2 points with a minimizing geodesic, so the length is equal to the distance, if every geodesic as the solution of a differential equation can be extended all over R, so there are no breakdowns and blow-ups of the solution of the differential equation, and if X as a global map is defined on all the tangent bundle, and if this space is metrically complete. These are all equivalent, and this is a very particular situation, but it can happen sometimes. Now, we can compute Taylor expansion on geodesics, and this is quite interesting. It will come up later when we go back to the Riemannian gradient descent. Now, this is just a computation, so it's not very difficult. Take a geodesic, so a solution of a geodesic equation, and take a C-infinity function on M. You compose the two functions, so you calculate h of t equal f of gamma of t. So you look at the function along the curve. And you write down your first order Taylor expansion. You already know it. The first order term is given by the scalar product at gamma 0 between the gradient of f and the tangent vector to the curve. If we want to go on, we need to compute the second derivative of h, which is the derivative of h prime, which is the derivative of what? H prime is at every point, if you just derive this expression, at every point is the scalar product between the gradient and the tangent vector. So, by the properties of the covariant derivative is this sum. But we are on a geodesic, so this term is 0. So you see the second order is given by a part which depends on how much the function varies in second order, and a part which is how much the curve varies on second order. And this is the curvature. But anyway, geodesic don't have this part. So you end up only with this part, which is written like that. So nabla gamma dot grad f, scalar product with gamma dot. So you can define the bilinear form on TPM given by this function, the scalar product between y and the covariant derivative in the x direction of grad f, of the gradient of f. And this is the Hessian of f, and usually denoted by nabla square of f. On a geodesic, you have this formula. So this is the scalar product between the gradient fv, which is just the differential of f applied to v. And this is the Hessian of f, so this expression, which surprisingly is symmetric in x and y, applied to v and v. So usually, the covariant derivative of a function is defined to be just the differential, so that you can write this down with all the nablas. So this differential of f becomes nabla f applied to v, and this is nabla square of f. The last part, in local coordinates, you can do the computations with the covariant derivative. You write everything down, you have fun with all your indices, and I just want to show you what you end up with. You end up with this expression. So this is a bilinear form, so it's a tensor product of differentials. The matrix that represents the Hessian in local coordinate is the Hessian of the function minus a correction depending on the Christoffel symbols of the matrix. So the Hessian is not something like the differential, which is defined intrinsically, but like the gradient depends on the metric, and the metric enters here, because here we used the fact that the metric is compatible with the covariant derivative, so we use the fact that we are using Levi-Civita connection. And so this is the expression of the Hessian in local coordinates, which is the Hessian of f in local coordinates plus minus actually a correction term. And I think this is enough for the first part.